work in Linux. All right. Okay, so we're recording. Welcome back to System Software. Today we are right in the middle of looking at files and file systems. Last time we went over the fundamentals of files in the kind of Unix-like world. Who read the Unix paper, or at least part of it? Not many people. Okay, that's too bad. Well, if you're interested in systems and you're interested in actually how this stuff was designed and the reasoning behind it, read this paper. It's a really good paper. It's a classic. You may have interview questions about this kind of stuff. It might help you in the future and to understand system design. It's a classic. I'd recommend reading it. All right, so homework 5 from the last time. Who has questions on this homework? No one? Everyone was good? Yeah.
Could you remind me if there was any difference between having the slash at the beginning and not having the slash at the beginning?
Oh yeah, there's a big difference. And so this was the kind of trick part of this questions here. So the slash at the beginning, what does the slash at the beginning signify? No, the root directory. So remember let me get the board from last time, which I also didn't put up. Let me get the board. Actually, it's here. Here. So the root of the file system is always called / /. And if you see a path that starts with /, it's an absolute path, which means you're given every single directory from the root that you need to enter in order to find this file. Does that answer your question? So if there is no /, then it's relative. And so how do you know the full path in a relative path? From the working directory. Exactly right. So if you have a relative path, that is, there's no / in front, then you just concatenate the working directory and the relative path.
And was there a difference between doing the / and not doing the /? I know you went over
Yes.
You have stuff in the if it overlaps with some sort of command in the path.
So the only so this doesn't have a / in front, so therefore it's not absolute.
Yeah.
It's a relative path. But this could easily have been if we had bin /user. It's the same kind of path as saying ./bin. It's just putting the name of a directory first. But the dot path is a special directory name. What does it refer to? Exactly, it refers to the current working directory. So putting dot here is the same as putting this here.
Yeah, is it just here it's not different from just not putting the /?
Yeah, I mean the file that you're referring to will be the same file. Yeah. It's the same. Yeah. It'll be the same. It'll be the same file. So.
It would just be different in cases where if you had a file called ls in your directory, you'd have to do ./ls to access it.
No, you can omit the ./ because it's the same path. I mean, it will go to the same file.
But ls refers to the command normally, right? So if you have a file called ls, then you want to refer to it.
Oh, I see what you're saying. That's only when you're running a file.
Yeah.
Is that what you meant?
Yeah.
Sorry, I misunderstood. Yeah. So ls, if you just type a command, it will search the path, search this environment variable that holds a set of directories to look for executables for. If you say /, it means the current folder, current working directory / the ls file, which doesn't exist. Good to get that clear. Yeah, you had a question?
So is it a difference using // versus seem to have, it doesn't seem to work differently. Is it only useful for like when we're programming something and we want to make sure we're getting something from our working directory?
Yeah. So
What I mean is it's
Yeah.
kind of redundant.
It is. So I could say dot dot. Yeah. So it just depends on whether whatever is processing your path. It's really just for the bash. The only case I can think of is in bash. When you give a file name, if you give a file name without a path, you just give the name of an executable, it's going to append these executable paths to your name. Otherwise, for most other tools, like, for ls itself, if I do ls dot slash, I mean, it also, so basically whenever you need to refer to your current directory without using an absolute path, that's when you need dot. So ls, for instance, if you run it without any arguments, it will, by default, use the current working directory. But let's say I want to list the parent directory and the current directory. Or I want to list the bin directory and I want to list the current directory at the same time. Well, how can I do that? How can I refer to the current directory? Well, I could do the absolute path, or I could use dot. Does that make sense as an example? So sure, by default, ls will use the current working directory, but if I want to refer to a series of paths, like the parent, bin, user, and the current directory, that's when I need a name for the current working directory. And so dot is that name. And so that's how you can refer to the current directory as a relative directory without having to resort to an absolute directory. Otherwise, you would have no way to do it. You'd have no way to refer to the current directory. There's no name for the current directory because you're already in the current directory. The name of it is in the parent directory's directory listing. So in the Unix style, this dot is an extra entry in your current directory entry to refer to the current directory. So you can name it. It's a way to give a name to the current directory, when otherwise you wouldn't have it in your current directory. So here, if I just say ls without the dot directory, none of these files refer to the syscalls directory. But by adding these special file names, I now have a path, an entry in my directory that refers to the current directory. This also goes back to how directories are implemented. If you remember, directories are implemented, they're just a mapping from a name to an inode number. And so this is the contents of the directory. The directory is just a directory listing, like a phone book. But if I had a whole series of phone books and I wanted to refer across them, then I could add that phone book into my current phone book. But what if I need to refer to myself, my own phone book? Well, then I'd need a special entry within the phone book to refer to itself. Maybe that's more confusing. I don't know. But does that answer your question? Did that answer it? Okay. Other questions about homework 5? Do you want me to? Oh, yeah.
Can you go to the last one? How come the working directory ends with a slash?
Oh, okay. This is just, so most processors don't care if you end with a slash or not. This is just me putting slash. It shouldn't matter.
Okay.
Because the tools that will concatenate them will account for the slash usually. So I will sometimes put a slash at the end to kind of signify that it's a directory instead of a file, but you definitely don't need to do that. So if you take this away, it's still going to be a directory. But that was just me, I don't know, not thinking clearly or something doing this. Questions on any of these entries? You want me to draw out any of these examples?
You don't mind.
Okay. You want me to just do the whole thing? Should I do the whole thing?
Yeah.
I'll do the whole thing. All right, let me... Get rid of this one. Okay, let's do this whole homework. Can anyone not read that? Can anyone not read it? Yeah. Yeah. So in other words, this working directory is irrelevant to absolute paths. So as we'll see when I go through this. All right, so let's do this. All right, so our working directory is slash, and we have the path slash home. So all file systems have a root, and where is home under this file system? What's it a child of? The root. So we've got home under here, and same thing for slash dev. We have slash, and we have for the root file system, for the root directory, and then we've got the dev directory underneath. All right, so here's the first kind of trick question. Our working directory is slash dev. Where does slash boot go? Does it go here, or does it go here? So who says it goes here? All right, who says it goes here under dev? No, it doesn't go under dev because those are the first trick question. Even though our working directory is slash dev, our path is an absolute path. So absolute paths always start from the root, ignoring the current working directory. So the absolute path tells us that if you start from root, the file is underneath the root directory. So boot is here and not here. Questions on that? So that's the key distinction between absolute and relative paths. So I'll preserve this here. Why is it not changing color? So put that to signify that's not the right path. All right, let's do the next one. So this is not really a trick question, but just sort of emphasize what working directories do. So our current working directory is slash, and we see the folder user or USR. Where does this go in the tree? Under the root, yeah, under the root. So we've got another folder under root here called USR. And I didn't specifically ask for this, but you could have done this. There's also, the dot and dot folders under each of these. So you could put those as well. All right, now we have the Paul folder. And is this absolute or relative? It's relative, as it says here, because there's no slash. So where does the Paul folder go on this tree? Under home, because the current working directory is slash home. And so notice I also put absolute paths for the current working directory. Otherwise, we'd have no way of knowing what its actual absolute path was. So Paul is under the home folder, which is under the root folder. Questions so far? All right, so let's look at a first, not really trick, but kind of testing whether you get the whole dot and dot folder stuff. All right, so what's our current working directory? Slash dev. So we are, and I wish I had a faster way to change this color. I'll use this green here to say, here's our current working directory. So here's our current working directory, dev. And we have dot slash home slash Paul slash source. So let's follow this through. We're here, is our current working directory. The dot folder, where does this take us? Right, to the parent, which is what folder? The root. So I'll put the dots and dots as needed. So dot is a directory entry under the dev folder, but when we say dot, it's a link or reference to the parent folder. So here's our working directory. We follow the dot folder, which is synonymous with going to the parent. And then we go to home, and then Paul, and this refers to the file called source under the Paul folder. Questions on that? So we started at slash dev. So slash dev, parent, the dot folder, which is a link with slash, the root, because that's the parent of dev, and then home, Paul, source. Yeah? Say it again? Did we have to draw the dot folder? No, you didn't have to draw it. You're not going to get any points off for drawing it. But it's a special folder. Remember we talked about links last time, hard links. So dot dot is a link. It's a synonym for slash. So yeah, that's I put this sort of dotted line to refer to these pointers or symbolic links, or I'm sorry, hard links to other files on the file tree. Questions on this so far? Okay, so if you got that, good. You've managed all the main kind of tricks of this, and if you didn't, then hopefully this makes clear the distinctions between absolute and relative and what the dot dot folder does, like operationally on the tree. Okay, so here's another hopefully straightforward one. We have the bin relative folder, relative directory. It's relative because our path does not start with slash. And our current working directory is user. Let's see if this actually works. Yeah, I don't know why I can't select with that. That's annoying. Okay, so now our relative directory is USR. And our working directory is USR, and our relative path is bin relative to the USR directory. So this is the bin folder. Questions on that one? Any other questions on that? All right, let's go to another working directory here. Our working directory is /home/Paul. So we have the slash folder, which is our root folder, home, Paul. So this is our current working directory. And we have the .bin folder. So this is also kind of testing this self-referential path. And I'll put the dot folder here to make it explicit what's going on. So this is a hard link to the Paul folder. So I'm in the Paul folder, I say /, and I'm referring to the Paul folder again. So this is a hard link that's synonymous with the Paul directory. So this is the / part, and then we have bin. So where is bin on this file tree? Or where is this bin referring to? Sorry, it's this one. This is the one I'm highlighting. Where is this bin on the file tree? Under Paul. So this is a separate folder called bin from this one. So this is what a hierarchical file system gets you. You can have multiple files named the same thing. And this is what relative paths do. You can just refer to the bin folder, and depending on where you are, your current working directory is, you may be referring to a different file or folder altogether. So if our current working directory were /user, then we'd be referring to this bin. Because our current working directory is this Paul directory, we're referring to a different bin directory, or file, I should say. Questions on this? Questions on this so far? All right, let's finish up. Our current working directory is /home/Paul. It's the same working directory. And now we're referring to the home directory. So this is a little trick question. So which home are we referring to here? There's already a home directory that we have drawn out on our file tree. Which home directory or home file is this relative path referring to? Yeah.
Anyone under Paul?
Yeah, a different one under Paul. So just to go over this again, our relative path is /, which is the root, home, Paul, and we refer to the home folder. That's a different file underneath the Paul directory, distinct from this file name underneath the root directory. All right, let's do the last one. So another kind of combining understanding the parent hard link with the fact that there are different, we can have the same file name under different directories. So here is our working directory. Let's do our working directory first. Our working directory is /dev .. which is synonymous with the parent, /home/Paul /home. So this is our current working directory. Questions on that? Let me go one more time. So The current working directory is /dev/ /, which is a hard link with dev's parent, /home, /paul, /home. So our current working directory is here. And now we just have a file named Paul, which is under this home directory. So you can see we have multiple files with the same name, but because they're in different directories, they don't necessarily refer to the same file. Questions? Questions on this? And I do post these boards online as well. So they're posted with here I put it under the board link. So I'll just put whatever I have on this whiteboard here online. All right, questions on this? So it's a good exercise to help you wrap your head around file systems, and you're using file systems all the time. So if you've ever been like, where's my file, or I don't know where it downloaded, or I don't know where to organize things or put things, you can use this tree-like structure to help you organize your code base. All right, any other questions on file systems? All right, let me stop recording and then we'll do attendance. All right. All right, let me start today's lecture. So today we're going to learn about system calls, or Syscalls for short. So just a quick reminder, what is system software? The definition I'm using in this class is software that bridges the kernel and applications. So just as a reminder from the introduction, we've got all our great computing hardware that electrical engineers and computer engineers design, the CPUs, memory, all sorts of peripherals, Ethernet cards. And we have all the applications that we want to be able to use this hardware for, like looking at cat videos, chatting with friends, gaming, doing actual work, going on the internet. And right above the hardware, we have this kernel layer, which I'll talk a little bit more about today. But this is really the subject of an operating system course. Well, how do you create this interface to the hardware? And the kernel provides a couple of useful things. It abstracts away hardware differences. So if you've got a flash drive versus a hard drive, you have a different protocol for communicating with that chip. The kernel will abstract that away and give you kind of a unified interface to storage, to memory. And the system software is what connects that idealized or abstract version of hardware to applications. So this is compilers, these are libraries. And so that's where system software sits. So questions on this? Questions on this so far? So I kind of covered this already, but kernel virtualizes hardware. It abstracts away differences. It does sharing between hardware resources. And it also protects hardware from users. So you as in user space, without say security exploits, you won't be able to directly touch the memory chip or directly touch parts of the hardware yourself. You can't directly instruct the CPU to jump to new code without being in some protected box. But this is more the subject of OS. And so there's this boundary called user space and kernel space. So I'm not going to go into this too much, but who's ever heard the terms user space, kernel space? So not much. You'll see this a lot when you take an OS class or if you deal with kind of low-level software. Kernel space is when the kernel is running. It runs in a mode that can access the hardware completely. User space is a mode of the hardware that will restrict access to certain instructions of the CPU. So when the kernel boots up, the last thing it does is it switches into user space and starts running user space applications. And when it does that, the CPU will actually restrict access to certain instructions that you can't use anymore. Instructions, and it'll also restrict access to directly accessing a memory. But anyway, don't worry about this too much. Take an operating system class if you want to learn how this layer is implemented and how the operating system is designed to actually do this. But for our purposes, the way we access hardware is through the kernel. And the way we access the kernel is through system calls. So system calls are just special function calls. From the programmer point of view, they look just like function calls. They are function calls. They're implemented a little differently under the hood. But they're just function calls into the kernel library. If you view the kernel as a library, just like when you call printf, you have this library code that does work for you. You just have to call the function. Kernel works in a similar way from the user space. So these are the functions that operate on this kind of idealized or abstracted hardware. And it allows you to ask the kernel to, say, give you access to the CPU, give you access to memory, give you access to files and other I/O. The way this is implemented is a little complicated. It's hardware dependent. But basically, here's a syscall called exec_ve. Normally, when you call a C function, and you've written a C function and you're calling a C function, normally what happens is we'll talk about how to implement functions, but you're basically jumping to another part of your code. You've written a function and it's compiled to machine code, and when you call a function, you're basically just jumping and running that other part of the program that you compiled. But with the syscall, it's a little different. There's a special, at least in x86, there's a special instruction called an interrupt, which is kind of like an event. It raises an event to the CPU, and when the kernel boots up, it registers these event handlers, and you select, and it effectively gives you a different event handler for each system call. And when you do this interrupt and the kernel handles it, the CPU will transfer the control into the kernel and also open up the kernel to all of the hardware operations that you as the user could not perform, like controlling memory, controlling the processor, controlling hardware. These are called interrupt handlers or trap handlers. So here, this is the code that the kernel developers wrote. This is the code that you wrote. And it's all living in memory, effectively at the same time. But the difference is this boundary between the kernel will switch between kernel mode and user mode. User mode where you have only restricted access to certain CPU operations, and kernel mode where you have basically unrestricted access to kernel operations. So questions on this? If you have an interest in actually how this works, take an OS class or read some of the resources that I put in the notes. So I put some notes on a OS textbook, operating system textbook, and there's some guides. I think I'll show these later. If you want to write your own operating system or you want to play with this at the hardware level, there's lots of open free guides that you can actually do this yourself. This is particular to x86, but most stuff above the really low level embedded or microcontroller layer has these protection modes at the hardware level. Questions on this? So in short, for our point of view, system calls are really just a special kind of function. That they operate the same way as a function from the user point of view, but they give us an entry point into the kernel code, which manages hardware. Yeah. Effectively, yeah, that's exactly right. So a lot of it says here, wrapper function. So a lot of the calls you do to operate on files or allocate memory, these under the hood are actually calling kernel code. And so in this class, you're probably used to using fopen, where you have this file abstraction. We're going to use the system call version, which is open. They're similarly named, but fopen will use open under the hood to actually call into the kernel, but we're going to do direct calls into the kernel, bypassing most library stuff, at least for the examples that I show you. But yeah, that's a really good point. The C library, a lot of it is wrappers for underlying calls. So printf, there's no kernel library call for printf. Instead, it's doing reads and write, or it's doing writes under the hood for you. All right, other questions? Other questions on this? Yeah.
What would be the benefit of using, like, say, a direct kernel call such as open versus open?
Well, I mean, for most applications, you probably just want to use the library call. But if you're, say, a library writer, or you don't like the behavior of printf, you want more direct control over I/O. So printf will do like buffering. It'll wait to actually call the kernel. There may be, or also if you're using a piece of hardware that doesn't behave like disk. So for instance, if you're doing network programming, you'll be using the low-level open and write, open and read, open write and read and write, or not open, they socket open, read and write calls. If you're doing, maybe working with other types of hardware, you'll do the direct calls on them. So remember we talked about last time, files are not just for storage, they're for basically any kind of I/O that you can imagine. There, if you read that Unix paper, which I know most of you didn't, the file abstraction is not just for storage, it's abstracting away I/O itself. So the open or the open read and write calls. So whatever piece of hardware you have, you can implement it as a file. So for instance, you can do direct reads and writes to raw memory if you'd like. You'll break stuff if you do that. You need kernel mode or root access to do that. But you could say make a new chip or have an embedded controller, hook it up to like USB or hook it up to a serial port. And if you had the right kernel module or the kernel code that would provide you the read and write abstraction, you could read and write directly bytes to that piece of hardware yourself. But for a lot of what we program, we use files. There's a lot of library code that's built up. That's the system software that's built up to avoid you having to do raw read and write operations. But in this class, we're going to write some, I'll show you next time, we're going to write some system code. We're going to write some utilities that will directly use kernel calls. We're going to do some direct file operations on the kernel. We'll actually look at those next time. Today we'll, depending on how much time I get to, this is broken across 2 lectures, so I'm going to go over a bunch of file system calls for managing storage today and next week. But good questions. Other questions on this? Okay, so in short, the kernel is really just a library for you to call into. Most of the time, you're not doing direct kernel calls. They're being mediated through the system software. They're being, when you're writing applications, like C applications, you're using printf or fopen, fread, fwrite. Those are calls into the system software. And so we're going to look at what calls the system software uses into the kernel to actually give you those convenience functions. I know programming in C, printf doesn't seem very convenient. It's also sort of onerous to work with in strings and memory and stuff. But there's even a more low-level type of programming before you get to the actual hardware. Okay, so covered some of this already, but system calls, they look, from our point of view, the programmer point of view, just like a C function. And the C library, which this diagram shows as wrapping the system call, will handle all of the entry into the kernel for you. So the kernel, instead of giving the name to the kernel, there's a number for each syst call. So this is this interrupt hex 80, or hex 80, I should say. Each of these system calls is assigned a number that's installed in a table that maps the number to where its location is in memory. And the C library for executing these system calls will handle all that kernel communication for you, because this is actually hardware dependent. If you have a different type of hardware, how you switch into kernel mode depends on the hardware you have. So ARM does something different from x86. So, but from our point of view, we just make a function call. It'll also give you the return values from the kernel, which are very, very simple and very, very low level. And the way you handle errors is also a bit different and a little bit more manual. It's kind of, think of it as like manual transmission versus automatic transmission. The C library is like automatically handling the kernel for you. When you're using the kernel calls, there's a lot of stuff you have to do on your own, like buffering, managing errors. Okay, so let's see what system calls we have available on our system. Let me go, well, I can do this on my own machine. It's a similar OS. So this does anyone remember what the man command does? Manual, yeah, it's the manual. So there is a list of all of the kernel system calls that are they're documented in here, that are available on our system. So there's a lot of them. But you'll notice that, say, I'm searching for fopen. Fopen is not here because it's not a system call. There's open, but no fopen. There's definitely no printf here, but there is a write call. So these are the library functions that the kernel provides us. And as a little kind of pro tip on man pages, because sometimes there are multiple commands or library calls or kernel calls that have similar names, like I just typed man open, I'm not getting the system call description. I'm getting this command called xgopen. This is a bash command for opening files. But we can, as the first argument, we can optionally tell the man page which section of the manual we'd like to look at. So looking at the man page for man itself, it tells you the numbers of the sections for its documentation. So section 1 is executable programs. This is your bash commands. Section 2, this is our system calls. Section 3, this is our library calls. So if we want to look at, say, the difference between open as a library call versus open as a system call, we can explicitly tell it to look for the name of that function in the corresponding section. So there is no C library call called open, but there is a system call in section 2 of our manual in the system call section called open. So this is the documentation of our system call open. Whereas if we want to see fopen, that's in our C library, which is in section 3. So this gives us the fopen documentation. Questions on that? So if you ever forget this, you can just type man, the manual page for the manual command, and review what section number corresponds. So this is all just designed by documenters. There's nothing like hard-coded into the actual kernel about this. This is the documentation system. Questions on this so far? Just as a quick refresher, so it does tell you here, help and quit. If you get stuck in this one of these man pages, just Q to quit. And if that doesn't work, hit escape. I think it's escape. Or hit escape or enter until you get back to this prompt that says Q to quit. You can use arrow keys depending on your terminal. You should be able to use arrow keys, page up, page down.
Is there a man quit?
What's that?
Is there a man quit?
Oh, you mean for the quit command? There's an exit command. There's several exit commands. You can also do -A to cycle through all of the sections that have a command with that name. So exit is a standard library call. When I quit, it'll prompt me to view the next one. It's also a system call. And yeah, those are the two. So there's, actually, isn't there there's a command called, oh, it's part of bash. Anyway, so there's two sections that have an exit command. So one is the standard library, and one is the system call. So they're actually two different calls when you do exit. But no, there's no quit command apparently, so man can't find it. But there's exit. So the bash program has built-in commands. One of those is called exit, and we'll build a bash interpreter as our project after file system. And so exit is one of the built-in commands. So some of the stuff you write on the shell is not a program. It's not part of the section 1 man pages. It's part of the built-in commands that bash can run. So exit is one of those. So yeah, there's basically 3 different exits in the system. All right, questions so far? So if you ever forget how to call one of these system calls, you forget its return values, you forget its exit codes, use the man page, man2, and I'll actually document these in each of the projects. So you'll have a table. Here's the syscalls you need for this project. Here's how you get to the man page. Here's the documentation in the Linux programming interface. I'll give that all to you as reminders, but just remember, man page, this is all self-documenting. It's all built into the system. You can review how to use these tools. And that also applies to the commands that I use in class. So if you forget the cat command, or you want to see other features of the cat command, or you forget ls, you want to see other features, you can use the man page for those as well. So remember, Q to quit, arrow keys to move yourself around, or Vim keys work as well. Okay, so I kind of showed this already, but section 3 are the C library calls, so that's why fopen is available there. But fopen, as your colleague pointed out, is a wrapper that uses the section 2 system call open. And here are examples of system calls. All right, questions on this so far? Questions on the concept? Yeah. Yes, I am. Thank you. I am recording. I have a little indicator here, which is on my screen, but not on that screen. Maybe I should make it go on the other screen so you guys can see. But yes, I'm recording. All right, so that's just to review, we have kernel mode and user mode. Kernel mode has unrestricted access to the hardware. User mode restricts access so that all hardware interactions have to go through the kernel. And this is so that no matter where you're writing your C program, it'll work on whatever hardware, different. Even if there's different hardware, you have a different implementation of storage, solid state versus spinning disk. The calls you make will go through the kernel, and the kernel will handle all of those hardware differences for you. So instead, you're programming this idealized hardware that the kernel provides you. And then, of course, the system software provides utilities like printf and other features that applications will use to not have to deal with the kernel. In this class, we're going to be actually writing system software. We're going to be writing that system software layer. So you'll see under the hood how your applications will use these useful system software tools. Okay, so let's talk about error handling. So one reason that learning system software is really good is it gets you in the mindset of error handling. It's very easy to forget to do error handling when you're working in high-level programming languages, especially scripting languages, where you just kind of don't worry about errors until the user runs your program and then they have a crash and then they'll come back to you and complain to you. But when you're developing, you may not be aware of different possible error states. But sound, good programming is managing errors and thinking about all possible inputs to your program, even ones that you don't expect or don't think should be inputs. So the Unix way of error handling is kind of DIY. You as the programmer have to do a bunch of manual work every time you do a system call to handle errors. And if you're really interested in kind of the history of systems, there's a really kind of famous section of an essay called "The Rise of Worse is Better," where there was a bit of a kind of Platonic kind of dialogue about the best way to do error handling, and kind of criticizing this developer onus of error handling in the system. But anyway, this is the system that won out. This is what most operating systems are built on, using this manual error handling. And this is where the system software comes in and can actually hide some of that error handling for you. But here we're going to open up the hood and see how this actually works. So read that paper. It's linked in the notes. All right. So there's two things you need to do whenever you do a system call. You have to check the return value. So that's kind of normal, right? When you do C programming, you check the return value to see what happened. But additionally, there is this special variable that gets set called the error number. So if everything goes well, this error number won't be set, and you can just move on with whatever return value you have, and just keep writing your program. But if there's any kind of error, this special value will be set. A special return value will be returned to you saying, "Hey, this system call did not work as expected." And you, as the programmer, have to do something about that. So on the one hand, this is onerous, but on the other hand, this allows you as the programmer to dictate how error handling should happen. So one easy thing to do is just always quit. But if you're writing software for a user, they may not want you to just crash every time an error happens. So even though you're probably not going to have to write system code, except for a small number of you, when you're writing applications, you should have this mindset as well. Error handling. What happens when unexpected input happens? What happens when whatever service we're communicating with doesn't work as expected? What's the user experience going to be? How is my application going to keep running even though my expectations are were violated by some component I'm depending on? Yeah.
Is this how high-level programming languages kind of dictate what error you have, whether it's syntax or whether it's some memory allocation error or something like that?
Yeah. So it's a second. So this is this how? What?
Yeah, is this like, for example, like C, is this how it dictates whether you have an out error or a calc error?
Yes. Yeah. Partially. So it's doing both. So it's looking at the kernel. So if you say have an out of memory error, which it can happen. I mean, probably nothing is going to work on your machine if you really do run out of memory. But your application can run out of memory. And so it's actually passing through to you saying, I can't do anything. There also may have its own errors that malloc or any system software can have its own errors as well. So for instance, for printf, if you give it a malformed string or something, or it can maybe detect that this string is not valid for this formatting string is not valid for me. But the low-level errors do definitely influence what the high-level software does. So let's say you're trying to open a file and it doesn't exist. You as the application developer can say, all right, the file doesn't exist, I'm just quitting. And the user has to rerun the program. But you could also imagine an interactive program where the file doesn't exist and you say reprompt the user for a new file name. Make sense? So just different strategies for handling errors. And even though this is a very low-level kind of manual transmission type of programming, it gives you this flexibility to decide how you want your program to recover from errors. So it's tedious, but it's a really good exercise in error management, which is pretty critical for any systems programming. Yeah.
Sorry, because in your webpage you have like the error open, so what's like the speed?
Oh, yeah, good question. I'll get to that as well. So there's some helper utilities to help you deal with errors as well. So this is the kind of classic, you'll see this in the Linux programming interface book. Basically, whenever you do a system call, it's not just call and get the return value, it's call it, check if I entered an error state, and then handle that error. So every time you're doing a system call, you need to have like 5 lines of code instead of 1. This is the tedium of doing system calls. You have to manage, you have to sort of proactively prepare for any possible error that can happen from that system call. Because somebody could like unplug a hard drive during your program execution. Your machine could shut down. The file may not be there as you expect. It may have been deleted since you started the program. So any system call, you should have error handling code that manages what happens when the call does not succeed as you expect. And this is what it looks like. Make the call, save the return value, check if the return value refers to an error state, which depends on the system call, and then handle the error. Now in this class, I think pretty much most of the time you're just going to exit. It just makes things easy. So you won't have to do any kind of fancy error handling. I think for the shell project, I'll have you like reprompt the user. But for the vast majority of time for this class, we'll do the simplest thing, which is to just print a message describing the error and then exiting. But even though that's what we're doing every time, we still have to do it. No one else is going to do it for us. We as the developers need to check for this error and tell the user. Otherwise, if we have a file, if we thought we opened a file and we go to read it, well, you're just going to get another error from the kernel. It's going to say, this file's not open, I don't know about this file. And the rest of your program is going to crash. Yeah, question? Was there a question? Yeah. This is a C program. Yeah, this is inside of a C program. So let me show the PRs, then I'll show some real code. But yes, this is C code. This is C code. So this is what you write in your C program. If that, yeah, just to make sure that wasn't clear. Other questions on this? Yeah.
So we're going to write all the kind of Syscalls.
Yeah, this will all be done in C. Yeah. Unless you have another preference for language. Rust, maybe? No. Yeah, it's all going to C. So like the Unix system was developed in tandem with the C language. So a lot of the support for this stuff is in C. There are sort of newer programming languages like Rust and Go, the systems programming language, which can also do this. But if you're working in like Python or something, you're not going to have direct access to these system calls except through a special, you could have a Python library that does it. Under the hood, the Python libraries are calling the kernel as well. But we're going to do this in C, the kind of classic systems programming language. All right, so how do we know what errors are possible and how do we know what return value to check? Well, this is where the man page comes in handy. There are two important sections to look at, and so this is something that actually the homework will test your memory on whether you remember this is where to look for the answers, because the answers are just here in the manual page. There are two, so first there's a description section describing its behavior, describes the inputs to the C code. This also, by the way, teaches you about good documentation. So if you're developing software for someone or developing a library, you want to tell them what the program does, what the inputs are, what the outputs are, and what the possible errors are. Your assumptions and what happens when those assumptions are violated. So that's kind of good documentation design. And then we have this section called return value and a section called errors. So return value, this is how we're going to know whether we need to handle the error. So if we don't see this return value, then we're fine. We can move on. If we're opening a file, we can go on to read it or write it or whatever we're doing. But if we see the return value as described in this return value section, then we know that the syscall did not succeed. So in this case for open, what's the return value that indicates an error? -1. And for a lot of syscalls, it's -1. So on error, -1 is returned, and error number is set to indicate the error. And then the error number is set to one of a long list of possible errors that the kernel could have encountered when it was running this. So just to show you how tricky it is to get even just an open command to work properly and all the things that can go wrong at the hardware and kernel level in order to get just you an open a file, which seems like a simple thing to us as the user, but there are a lot of things that can go wrong. So one is, you tried to create a new file when you opened it, but it already exists. So I'm not going to create a new file when you told me to create a new file because it already exists. Let's see some other ones. So you're trying to read and write to a file, but it's actually a directory. So I'm not gonna write to that. Path name was too long. So there are limits on sizes of file names in the system. So anyway, basically, every possible case that the kernel can encounter is reflected in these errors and passed along by the kernel to you. So this is why the rise of worse is better kind of dialogue happened, because it was like, well, why are we making the programmer or the user subject to these errors? And there's design arguments for how you do this. So think of it as kind of low-level manual transmission type of programming. Yeah.
Are there any chances that you run into an error that's not documented?
It's a good question. I mean, it's sort of a philosophical question. I guess like someone could unplug the machine, and your program's not running anymore. I think if that happens, it means the kernel designers didn't think through every case. I would think there would have to be a bug. That would be like a bug in the kernel, or the hardware did not satisfy its requirements. So you got some sunspot caused your bits to flip when you were doing an operation, and as the kernel designers assume that the hardware works correctly. So if the hardware didn't actually work correctly, and it is doing error handling for some hardware stuff, but it's possible that. But we would just call those a bug. We'd call those a bug in the hardware, a bug in the kernel. So sure, it's certainly possible. But I guess the question is, philosophically, are these covering all of those possible cases? And I think so, because the programmer is defining what open does. Open is supposed to do what it says here, open a file and make it available for reading and writing. And so as long as it supports that, and it does that, then everything else is an error. So anything not caught, I mean, in the code they write, just everything else is caught as an error. So, sort of logically when you write code, and I recommend this for everyone, if you put an if statement, you're checking a condition, don't leave the else branch blank. Don't leave it empty. Cover every possible case of your program, and that'll go a long way to making sure you have correct code. So it's very easy to forget about certain cases, but if you're writing an if statement, that's where the cases come from in code. So always have an else branch, even if it's just a comment that says, "Hey, I should do nothing." But that way, you'll be prepared against unexpected inputs to your program. But yeah, that's a good question. I don't know how to philosophically answer that. We would call those bugs if it doesn't work as behaved. So it's certainly possible for it not to work as expected. But usually, when we have bugs in programming, it's not the hardware, it's not the kernel. Usually, it's us, the programmer. Usually. All right, questions on this so far? Questions on error handling? Yeah.
Why do we have two different variables for indicating an error? Can't you just put the error code in the return value itself?
Yeah, I think you could. Yeah, I don't know. That's a good question. It's probably answered in here. Yeah, that's a good question. I'll have to think about it more. Ask on EdSTEM, and I'll dig up a resource to see why that is. Maybe it's it may either be like a concurrency thing or a size of data thing. It may just be easier to write that way. I'll have to look. But ask on EdSTEM. It's a good question. Okay, so this is error handling. This is the documentation of it. All right, there is a helper function called p-error, which your colleague was asking about, which will basically write an error message for you. So instead of having to write out, do fprintf to write it out, we just call p-error with a name, and it'll prefix the error message with whatever name you give. By convention in the Linux programming interface, you just give the name of the system call that you were calling, and then it will look at the error number and write a English language message for you, a human language message for you, interpreting that. So this kind of reduces a little bit of the burden of error handling if you just want to report a error message and exit. But this is the pattern of calling system calls for almost all syscalls we do in this class. Call the system call, check whether its return value was an error, and then call p-error to interpret the return value and exit in almost all cases. Questions on this? All right, let's take a look at a full example. So here's my kind of standard C program. I'll give you the headers you need for all of these. So I've sort of commented where there's a lot of different headers where these things are defined. We have a basic main function. It reads in one argument. If the argument is not there, then we print out. This is kind of a lightweight version of the kind of classic Unix interface where by default, it's going to tell you the usage, and we exit. Any questions on this part of the C code? Hopefully this looks mostly familiar to most people. Yeah?
Why do we check if RC is less than?
Oh, so this is so this is command line arguments. Who learned about command line arguments in previous C classes? Okay, only like half. All right, let me go over command line arguments quickly. So if you look at remember our command line class where we had these tools like ls, and we could pass ls arguments. So I could say, well, I don't want to look at my current folder, I want to look at /bin. So what bash will do is it will take this string and it'll break it up into tokens. It'll give you the name of the argument, and then it'll break each of these up basically by white space, more or less. and give you 3 arguments to this ls command. It'll take this string and it'll pass it here to argc and argv. So argv will have something like, it'll be a string, an array of strings that looks something like this. So bash will take this command, and when it calls the main method of the ls program, it'll pass this. Because in C we don't have a string type or an array type that's has a predefined size, it'll also pass. Actually, I think this is null terminated. Maybe, I don't remember, but I think it probably should be. It'll pass also the number of elements in this array. Questions on that? Hopefully, who's seen C arrays? Everyone hopefully has seen C arrays. No? Who's never seen C arrays before? Arrays in C. Okay. So yeah, this gives you a listing of the command line arguments. So it gives you, including the name of the program. So it doesn't just give you the stuff after the name of the program. It gives you the name of the program too. So it gives you these 4 tokens and argc. So the reason I say less than 2 is because if I want a single argument, then this list is going to be how large, how long? 2. It's going to have 2 elements in it. It's going to have the name of the program and the argument name. Command line argument, yeah.
So for the char array, the first, well, I guess the 0 index is the actual program.
Exactly.
First argument.
That's right. Yeah. This is the program name. And then, yeah, the rest of them. So kind of first argument. So the naming is maybe a little confusing. Other questions on argument processing? So I can actually show you what this looks like. Do I have printf? Yes, I do. Let's do it like this. So I'm going to loop over all the arguments, and you can see what this. Did I break anything? No. So here I just looped over all the arguments and printed them out. And so you can see here, this was my, This was my input here. Let's make this full screen. This was my input, these 4 tokens. And you can see argv0 is this, argv1 is this. Hello, world 4. Questions on that? So that's the argument processing stuff. Okay, and then you can see if I only give a single one, it triggers this branch. Okay, so let's take a look at the error handling code. Oops. All right, so what does this program do? This is exactly what we showed in the slides. It tries to open a path. It gives the read-only flag. So the later kernel calls like write and read will check these flags. And then if any error happens in opening, I'm going to call p error to report the error. Otherwise, I'm going to call the close syscall, which tells the kernel that I no longer want to operate on this file. And if the close command fails, I'm going to print out any errors from that. Okay, so let's try putting a file that exists, like errornode.c. So errornode.c exists, and I didn't recompile it. Let me take out that. I commented that stuff out. So you can see nothing happens here. You can't see anything happening because neither of these branches were hit, so nothing's being printed out. So I could, in keeping with, so for this is special code. It's a place where people don't put else branches because this always exits. But I'll put here, successfully open the file. Oof. So you can see that it didn't hit this branch. But if I trigger one of the error conditions, like let's say trying to open a file that doesn't exist, then I don't hit this branch, or I don't hit this code because I entered this branch. The return value of open was -1, indicating an error, and the error state corresponding to file doesn't exist was triggered, and p error took whatever string I put in here, open, printed it out with a colon, and then converted that error number into a string. Questions on this? And I've also got some, so there's a cool command called strace, which will show you all of the system calls that get executed during the execution of a program. It traces the system calls. So there are a lot of other system calls, but I'm just going to show you the ones we're looking at in class today: open, close, exit, etc. So here's the system calls that get triggered when within these names when I call missing file. So open gets called. So these are for dynamic library loading stuff. Don't worry about this. This is our call to open that we have in our program, and you can see it tells you what the return value is and what the error no code is. And notice that even though I've checked for p error is not a system call. So no p error happens here. We have a call to close, which is actually automatic for any open files you have, and then exit is wrapping this exit group call. But you can see our system call here, where it's actually happening here. And let's do a file that does exist to see if I don't think there should be any differences. So you can see here that this call succeeds, gives us a return value of 3, and no error state from this syscall. Okay, so that's our first system call and our first full program using a system call. We're doing error checking using p error. For now, we'll do that for almost all the system calls we do. And that's it. So it looks very much like fopen, but what difference do we have here? What's different here from fopen, if anyone can remember? We can use the man page to tell us. We can use the man page to tell us, well, it has a bit of a different interface. It returns this file data structure instead of an integer. We just get an integer back from this open. What are we going to do with an integer? How are we going to read and write to an integer? Well, there's a file descriptor, and it's what the kernel itself internally uses to keep track of what files your process has open. And we'll talk about that more next time when we go to actually reading and writing files. But under the hood, the kernel is tracking for each process what files it has open. It gives them a number, and you as the developer have to refer to that number whenever you want to do any operations on files. All right, let's leave it at that. Let me know if you have any questions, and see you next time.